So as we move on, we're going to look at one more of the functions that have been built into our calculators. It's another powerful function that's been built in to help us with some of the normal distribution work and problems that we're going to be looking at. So far, we've looked at how to standardize a normal distribution so that we can make use of the tables. So we use the standardization formula to generate a z-score. We've looked at how the tables are useful for finding probabilities that match z-scores, and we've used the alternate tables to find z-scores that match probabilities. Now both of these can be used forwards and backwards, so there's quite a lot that we can do with just the tables. But once again, the calculators are really powerful, really useful, and we want to optimize the time that it takes for us to work on a certain problem. So today we're going to look at the inverse normal distribution function. The inverse normal distribution function allows us to find unknown real-world values as long as we knew something about either the probability above that value or the probability below that value. We could also use this on the standardized distribution, the distribution where the mean is 0 and the standard deviation is 1. And in that case, it will be helping us to generate z-scores exactly like we did in the tables. So look out for opportunities to do that, and maybe that would save you even having to reference the tables in the first place. Some of the best A-level students are able to do a lot of this work on their calculators because primarily they have a well-structured diagram in front of them, and by well-structured I mean they're labeling the probabilities, they're labeling the mean, and they're labeling the real-world values or the Z values that we might be interested in. On top of that, they understand and appreciate what the tables did, and they know how to replicate that on their calculators. Okay, so in general, we're trying to find an unknown value of A as long as we know something about the probability. So in this case, what is the unknown value A? If I know the probability that X is less than A equals 0.8. So what does that look like on a diagram? Well, where do I even mark A? I know that the middle, the mean, has 50% below it. So I would need to move to the right to have more than 50%. So here's 50% and below. This would maybe be 70, 60% and below. And then A is roughly in a good place to say that this is 80% below. So I'm going to shade in. Even just thinking about the amount you shade, the majority of the graph should be shaded. 80% of the graph should be shaded. Okay, so for this particular normal distribution, mean is 30, standard deviation is 4, and I want to find A. I could have used the inverse tables because I know there's 20% above, and you can maybe do that to check your answer, but I'm going to show you how to use the inverse normal function. It's in a similar place as we've seen before, so options, statistics, distribution, normal, but this time you're going to press inverse normal, INVN. We're going to press inverse normal. The syntax that we're expected to put in, and be really careful here, we need the probability. Well, which probability? For this method, we should always put the probability to the left, so the probability that it's lower than the value we're looking for. So the probability to the left, which is 80%, and then standard deviation and the mean. In this case, and you should have your calculator in your hand right now, we're going to type in inverse normal, 0.8, 4, and 30. Just hit enter, and we should all get the same answer. The answer in this is 33.3665. And as usual, let's just do a quick sense check. Would that number make sense? Well, we know that the median, the mean, the middle number was 30, and A should be bigger than 30. So in that initial instance, I'm confident that this is a sensible answer. Always do the sense check. It's just your first indication that you are on the right path, that your working out is correct, and that you're working in a sensible region. Okay, so let's check in with a few more examples. This time round, we're working with a normal distribution where the mean is 20 and the standard deviation is 3. We've been asked to find the unknown value of A, so a real world value A, where the probability that X is less than A is 75%. So the probability is 3/4. You should instantly realize that we're talking about the upper quartile, a value that has 75% below it and 25% above it. All right, just the kind of thing that I want you to think of as you work with and read some of these questions and probabilities. Okay, so 20 is in the middle. I can put in my upper values and my lower value, and just trying to figure out exactly where A should be. Not even exactly, just roughly where A should be. I know that there's 75% below it. The mean has 50% below it. I would need to move to the right hand side to get 75% below. I want a large proportion below this value and only a small proportion above. Okay, so from there I know that I'm using the inverse function. I want the probability on the left. That probability is 75%. So I'll type in 0.75, 3 and 20. Okay, straight into the calculator. A should equal 22.0235. Sense check, I wanted it to be bigger than 20. I'll go with that. I also knew that I expected it to be less than 1 standard deviation away from the mean, and 2.02 is just a little bit less than 3. So there's a second level of sense check that I'm able to provide myself with there. Okay, let's move on to the next question. So part B, we want the probability that x is greater than A equals to 0.4, and we're looking for that unknown value of A. So let's get the diagram correct. I'm looking for greater than wherever I mark on the diagram. So I'm actually going to be marking to the right hand side. Wherever I place A, I'm looking for the space above A. And if I went to the mean, the space above that is 50%. I don't want that much. I want it to be less than half above the value that I place. So I know A must be on the right hand side. Okay? A must be on the right hand side to make the diagram show 40% being above A. Once again, we're off to our calculators, but we're not using that 40%. As I said before, we want the probability to the left, and the probability to the left is 60%. 60, 3, 20, plug it all into the calculator, hit the equals button, and we get that A equals 20.76. Alright, so a sense check there is actually going to tell me whether or not I've gone onto the right side of the diagram. I'm worried some people would have put in 0.4, but the answer you got would have been below 20. The answer you got would have maybe been 19 point something. It would have been 19.24. But that immediately should be an alarm bell to let you know that you haven't quite entered the right values. So make sure you do the sense check. This, once again, lets you know if you're on the right track or not. Okay, and then something a little bit different this time round. We're looking at question C. So we've been told that the probability that x is in between 16 and A is 0.3. So it's a double-sided probability statement. Let's start by getting the diagram for this. 16 is going to be less than 20, and just from experience, I think I'm going to place A on the left-hand side as well. 30% is quite low. I'm not sure 16 to 20 would be as small as the 30%. Anyway, that's beside the point. Now, to use the inverse function the way that we have, I need to know the probability from A all the way down to the bottom tail. So I'm going to find the probability that is less than or equal to 16, which by now we can quite easily do on our calculators. So the probability x is less than or equal to 16 is 0.0912. Now I can add that into the diagram, and then I can generate a statement for the probability that x is less than A, just like we've done in the previous questions, just by adding the value I've just got onto 0.3. So now I'll write my own statement. The probability that x is less than A is 0.3912. Now this is perfect for the inverse function, so I'll go ahead and put this straight into that inverse function. So making sure that it's the probability on the left of A, which is what we just found by combining those two previous probabilities, and that leads to an answer of 19.1714. And like I said, it does match up with the diagram that and A is below the mean. This will come with experience, but even if you got it on the right hand side, once you realize what the value is, that will let you know you can maybe redraw your diagram and move on from there. So let's just do one more. This time it's a question in context. We're told that plates are made where they have a diameter which can be modeled by the normal distribution, where the mean is 20 and the standard deviation is 1.5. Given that 60% of the plates are less than X centimeters, let's find X. Okay, as always, I'll start by defining the distribution. I'll get myself a nice diagram. I'm going to label this with the mean. Let's get that right in the middle. Now, where would I put X so that 60% are below X? Well, I know that 50% are below the mean. So for 60% to be below X, X needs to be off towards the right hand side. So X, I'm just going to label right here. And I'm shading in 60%. It should be more than half that I'm shading in. I'm shading in 60%. Okay, so quite straightforward. We're going to use the inverse function with the 60%, the standard deviation, and the mean. And that gives us an answer of 20.38. So 60% of the plates are less than 20.38 centimeters in diameter. Second part of the question, find the interquartile range. Alright, so I mentioned earlier, and you should know already, what percentages relate to the interquartile range. The lower quartile has 25% below it, and the upper quartile has 25% above it. Alright, that should be useful. Lower quartile over here, I can mark on the percentage. The upper quartile, once again, I can mark on the percentage. Alright, the lower quartile should be the more straightforward of the two. I know that I'm going to use the inverse function and 25% along with the parameters 1.5 and 20. And that gives us a lower quartile of 18.9883. The upper quartile, we might have to think a little bit more about this. There's 25% above. A lot of people are tempted, once again, to use that 25%. But I'm trying to drill into your heads. I'm trying to make you remember, and for you to instinctively know, we want the probability to the left, which is going to be 75%. So you need to be quite fluid and fluent with choosing the right probability, with generating 75% from 25%. Okay, inverse function, very much the same, with a 75% in the first space, and that gives us an upper quartile of 21.0117 centimeters. Upper and lower quartile, because we knew 25% and 75%. The question won't give that to you. They expect that to be base knowledge around quartiles, which we worked quite extensively with in year 12.